The FGM-148 Javelin is an American man-portable fire-and-forget anti-tank missile fielded to replace the M47 Dragon anti-tank missile in U.S. service. It uses an automatic infrared guidance that allows the user to seek cover immediately after launch, as opposed to wired guided systems, like the Dragon, where the user has to actively guide the weapon throughout the engagement. The Javelin's heat warhead is capable of defeating modern tanks by attacking them from above, and is also very useful against fortifications in a direct attack flight. Overview: Javelin is a fire-and-forget missile with lock-on before launch and automatic self-guidance. The system takes a top attack flight profile against armored vehicles, but can also take a direct attack mode for use against buildings, targets inside the minimum top attack engagement range, and targets under obstructions. This missile also has the ability to engage helicopters in the direct attack mode. It can reach a peak altitude of 150 meters in top attack mode and 60 meters in direct fire mode. It is equipped with an imaging infrared seeker. The tandem warhead is fitted with two shaped charges, a precursor warhead to detonate any explosive reactive armor and a primary warhead to penetrate base armor. The missile is ejected from the launcher so that it reaches a safe distance from the operator before the main rocket motors ignite. A soft launch arrangement. This makes it harder to identify the launcher. However, backblast from the launch tube still poses a hazard to nearby personnel. Thanks to this fire-and-forget system, the firing team may change the position as soon as the missile has been launched, or prepare to fire on the next target while the first missile is still in the air. The missile system is most often carried by a two-man team consisting of a gunner and an ammo bearer, although it can be fired with just one person if necessary. While the gunner aims and fires the missile, the ammo bearer scans for prospective targets, watches for threats, such as enemy vehicles and troops, and ensures that personnel and obstacles are clear of the missile's backblast. Development. In 1983, the United States Army introduced its AAWSM requirement, and, in 1985, the AAWSM was approved for development. In August 1986, the proof of principle phase of the development began, with a $30 million contract awarded for technical proof demonstrators. Ford Aerospace, Hughes Aircraft Missile System Group and Texas Instruments. In late 1988, the POP phase ended and, in June 1989, the full-scale development contract was awarded to a joint venture of Texas Instruments and Martin Marietta. The AAWSM received the designation of FGM-148. In April 1991, the first test flight of the Javelin succeeded, and in March 1993, the first test firing from the launcher succeeded. In 1994, low levels of production were authorized, and the first Javelins were deployed with U.S. Army units in 1996. Test and evaluation. Development test and evaluation is conducted to demonstrate that the engineering design and development process is complete. It is used to reduce risk, validate and qualify the design, and ensure that the product is ready for government acceptance. The DT and AMP-E results are evaluated to ensure that design risks have been minimized and the system will meet specifications. The results are also used to estimate the system's military utility when it is introduced into service. DT and AMP-E serves a critical purpose in reducing the risks of development by testing selected high-risk components as subsystems. DT and AMP-E is the government developing agency tool used to confirm that the system performs as technically specified and that the system is ready for field testing. DT and AMP-E is an iterative process of designing, building, testing, identifying deficiencies, fixing, retesting, and repeating. It is performed in the factory, laboratory, and on the proving ground by the contractors and the government. Contractor and government testing is combined into one integrated test program and conducted to determine if the performance requirements have been met and to provide data to the decision authority. The General Accounting Office published a report questioning the adequacy of Javelin testing. The report is called Army Acquisition. Javelin is not ready for multi-year procurement, opposed entering into full-rate production in 1997 and expressed the need for further operational testing due to the many redesigns undergone. In 1995, Secretary of Defense William Perry had set forth 5 new operational test initiatives. These included: 1. Getting operational testers involved early in development. 2. Use of modeling and simulation. 3. Integrating development and operational testing. 4. Combining testing and training. And 5. Applying concepts to demos and acquisitions. The late-phase development of the Javelin retroactively benefited from the then new operational test initiatives set forth by the Secretary of Defense, as well as a further test conducted as a consequence of the Army's response to the GA report. Before the Milestone 3 decision, and before fielding to 3rd Battalion, 75th Ranger Regiment at Fort Benning, the Javelin was subjected to limited parts of the 5 operational test and evaluation initiatives, as well as a portability operational test program, which included live firings with the full-rate configuration weapon per initiatives and as a DT and AMP-E function. The Institute for Defense Analyses and the Defense Department's Director of Operational Test and Evaluation became involved in 3 development test activities, including: 1. Reviewing initial operational test and evaluation plans. 2. Monitoring initial operational test and evaluation. And 3. Structuring follow-on tests and evaluation activities. The results of these efforts detected problems and corrected significant problems, which led to modified test plans, savings in test costs, and GA satisfaction. Qualification testing. The Javelin Environmental Test System is a mobile test set for Javelin all-up-round and the Command Launch Unit. It can be configured to functionally test the AUR of the CLU individually or both units in a mated tactical mode. This mobile unit may be repositioned at the various environmental testing facilities. The mobile system is used for all phases of Javelin qualification testing. There is also non-mobile jets used for standalone CLU testing. This system is equipped with an environmental chamber and is primarily used for product verification testing. Capabilities include Javelin CLU testing, Javelin AUR testing, Javelin mated mode testing, Javelin testing in various environmental conditions, and CLU private. The all-up-round test sets include extreme temperature testing, missile tracker testing, seeker, focal plane array testing, pneumatic leakage, continuity measurements, ready time, and guidance sections. Components: missile warhead. The Javelin missile's tandem warhead is a heat type. This round utilizes an explosive-shaped charge to create a stream of superplastically deformed metal formed from trumpet-shaped metallic liners. The result is a narrow high-velocity particle stream that can penetrate armor. The Javelin counters the advent of explosive reactive armor. Era boxes or tiles lying over a vehicle's main armor explode when struck by a warhead. This explosion does not harm the vehicle's main armor, but causes steel panels to fly across the path of a heat round's narrow particle stream, disrupting its focus and leaving it unable to cut through the main armor. The Javelin uses 2 shaped charge warheads in tandem. The weak, smaller diameter heat precursor charge pushes through the era without setting it off, and punches a channel through it for the much larger diameter heat warhead, which then penetrates the target's primary armor. A two-layered molybdenum liner is used for the precursor and a copper liner for the main warhead, to protect the main charge from the explosive blast, shock, and debris caused by the impact of the missile's nose and the detonation of the precursor charge. A blast shield is used between the two charges. This was the first composite material blast shield and the first that had a hole through the middle to provide a jet that is less diffuse. A newer main charge liner produces a higher velocity jet, while making the warhead smaller. This change makes it more effective, leaving more room for propellant for the main rocket motor, and thus increasing the missile's range. Electronic arming and fusing, called electronic safe arming and fire, is used. The ESAF system enables the firing and arming process to proceed, while imposing a series of safety checks on the missile. ESAF cues the launch motor after the trigger is pulled. When the missile reaches a key acceleration point, the ESAF initiates a second arming signal to fire the flight motor. After another check on missile conditions, ESAF initiates final arming to enable the warheads for detonation upon target impact. When the missile strikes the target, ESAF enables the tandem warhead function. Though the Javelin's tandem heat warhead has proven efficient at destroying tanks, most threats it was employed against in Iraq and Afghanistan were weapon crews and teams, buildings, and lightly armored and unarmored vehicles. To make the Javelin more useful in these scenarios, the Aviation and Missile Research, Development, and Engineering Center developed a multi-purpose warhead for the FGM-148F. While it is still lethal against tanks, the new warhead has a naturally fragmenting steel warhead case that doubles the effectiveness against personnel due to enhanced fragmentation. The MPWH does not add weight or cost and has a lighter composite missile mid-body to enable drop-in replacement to current Javelin tubes. Propulsion. Most rocket launches require a large clear area behind the gunner to prevent injury from backblast. To address this shortcoming, without increasing recoil to an unacceptable level, the Javelin system uses a soft launch mechanism. A launch motor using conventional rocket propellant ejects the missile from the launcher, but stops burning before the missile clears the tube. The flight motor is ignited only after a delay to allow for sufficient clearance from the operator. To save weight, the two motors are integrated with a burst disc between them. It is designed to tolerate the pressure of the launch motor from one side, but to easily rupture from the other when the flight motor ignites. The motors use a common nozzle, with the flight motor's exhaust flowing through the expanded launch motor, because the launch motor casing remains in place. An unusual annular igniter is used to start it. A normal igniter would be blown out the back of the missile when the flight motor ignited and could injure the operator. Since the launch motor uses a standard NATO propellant, the presence of lead beta-resorcinol as a burn rate modifier causes an amount of lead and lead oxide to be present in the exhaust. For this reason, gunners are asked to hold their breath after firing. In the event that the launch motor malfunctions and the launch tube is overpressurized, for example, if the rocket gets stuck, the Javelin missile includes a pressure release system to prevent the launcher from exploding. The launch motor is held in place by a set of shear pins, which fracture if the pressure rises too high and allow the motor to be pushed out the back of the tube. Seeker as a fire fire-and-forget missile. After launch, the missile has to be able to track and destroy its target without the gunner. This is done by coupling an onboard imaging IR system with an onboard tracking system. The gunner uses the CLU's IR system to find and identify the target, then switches to the missile's independent IR system to set a track box around the target and establish a lock. The gunner places brackets around the image for locking. The seeker stays focused on the target's image, continuing to track it as the target moves, as the missile's flight path alters or as attack angles change. The seeker has three main components: focal plane array, cooling and calibration, and stabilization. Focal plane array. The seeker assembly is encased in a dome that is transparent to long-wave infrared radiation. The IR radiation passes through the dome and then through lenses that focus the energy. The IR energy is reflected by mirrors onto the FPA. The seeker is a two-dimensional staring FPA of 64 × 64 Mercad detector elements. The FPA processes the signals from the detectors and relays a signal to the missile's tracker. The staring array is a photovoltaic device where the incident photons stimulate electrons and are stored pixel by pixel in a readout integrated circuits attached at the rear of the detector. These electrons are converted to voltages that are multiplexed out of the ROIC on a frame-by-frame basis. Cooling, calibration. The FPA must be cooled and calibrated. The CLU's IR detectors are cooled using a Dewey flask and a closed-cycle Stirling engine, but there is insufficient space in the missile for a similar solution. So, prior to launch, a cooler mounted on the outside of the launch tube activates the electrical systems in the missile and supplies cold gas from a Joule-Thomson expander to the missile detector assembly while the missile is still in the launch tube. When the missile is fired, this external connection is broken and coolant gas is supplied internally by an onboard argon gas bottle. The gas is held in a small bottle at high pressure and contains enough coolant for the duration of the flight of approximately 19 seconds. The seeker is calibrated using a chopper wheel. This device is a fan of 6 blades, 5 black blades with very low IR emissivity and 1 semi-reflective blade. These blades spin in front of the seeker optics in a synchronized fashion such that the FPA is continually provided with points of reference in addition to viewing the scene. These reference points allow the FPA to reduce noise introduced by response variations in the detector elements. Stabilization. The platform on which the seeker is mounted must be stabilized with respect to the motion of the missile body, and the seeker must be moved to stay aligned with the target. The stabilization system must cope with rapid acceleration, up, down and lateral movements. This is done by a gimbal system, accelerometers, spinning mass gyros, and motors to drive changes in position of the platform. The system is basically an autopilot. Information from the gyros is fed to the guidance electronics which drive a torque motor attached to the seeker platform to keep the seeker aligned with the target. The wires that connect the seeker with the rest of the missile are carefully designed to avoid inducing motion or drag on the seeker platform. Tracker. The tracker is key to guidance control for an eventual hit. The signals from each of the 4096 detector elements in the seeker are passed to the FPA readout integrated circuits, which reads then creates a video frame that is sent to the tracker system for processing. By comparing the individual frames, the tracker determines the need to correct so as to keep the missile on target. The tracker must be able to determine which portion of the image represents the target. The target is initially defined by the gunner, who places a configurable frame around it. The tracker then uses algorithms to compare that region of the frame based on image geometry. and movement data to the new image frames being sent from the seeker, similar to pattern recognition algorithms. At the end of each frame, the reference is updated. The tracker is able to keep track of the target even though the seeker's point of view can change radically in the course of flight. To guide the missile, the tracker locates the target in the current frame and compares this position with the aim point. If this position is off-center, the tracker computes a correction and passes it to the guidance system, which makes the appropriate adjustments to the 4 movable tail fins, as well as 8 fixed wings at mid-body. This isn't autopilot. To guide the missile, the system has sensors that check that the fins are positioned as requested. If not, the deviation is sent back to the controller for further adjustment. This is a closed-loop controller. There are 3 stages in the flight managed by the tracker. 1. An initial phase just after launch. 2. A mid-flight phase that lasts for most of the flight. And 3. A terminal phase in which the tracker selects the sweet spot for the point of impact. With guidance algorithms, the autopilot uses data from the seeker and tracker to determine when to transition the missile from one phase of flight to another. Depending on whether the missile is in top attack or direct attack mode, the profile of the flight can change significantly. The top attack mode requires the missile to climb sharply after launch and cruise at high altitude, then dive on the top of the target. In direct attack mode, the missile cruises at a lower altitude directly at target. The exact flight path, which takes into account the range to the target, is calculated by the guidance unit. Launch tube assembly. Both men carry a disposable tube called the launch tube assembly, which houses the missile and protects the missile from harsh environments. The tube also has built-in electronics and a locking hinge system that makes the attachment and detachment of the missile to and from the command launch unit a very quick and simple process. Command Launch Unit. The gunner carries a reusable command launch unit, more commonly referred to as a CLU. The CLU is the targeting component of the two-part system. The CLU has 3 views which are used to find, target, and fire the missile. The CLU may also be used separately from the missile as a portable thermal sight. Infantry are no longer required to stay in constant contact with armored personnel carriers and tanks with thermal sights. This makes infantry personnel more flexible and able to perceive threats they would not otherwise be able to detect. In 2006, a contract was awarded to Toyon Research Corporation to begin development of an upgrade to the CLU, enabling the transmission of target image and GPS location data to other units. Day field of view. The first view is a 4x magnification day view. It is mainly used to scan areas for light during night operation, because light is not visible in the thermal views. It is also used to scan following sunrise and sunset, when the thermal image is hard to focus due to the natural rapid heating and/or cooling of the Earth. WFOV. The second view is the 4x magnification night view, and shows the gunner a thermal representation of the area viewed. This is also the primary view used due to its ability to detect infrared radiation and find both troops and vehicles otherwise too well hidden to detect. The screen shows a grayscale view which can be adjusted in both contrast and brightness. The inside of the CLU is cooled by a small refrigeration unit attached to the sight. This greatly increases the sensitivity of the thermal imaging capability, since the temperature inside the sight is much lower than that of the objects it detects. Due to the sensitivity this causes, the gunner is able to focus the CLU to show a very detailed image of the area being viewed by showing temperature differences of only a few degrees. The gunner operates this view with the use of two hand stations similar to the control stick found in modern cockpits. It is from this view that the gunner focuses the image and determines the area that gives the best heat signature on which to lock the missile. An FOV. The third field of view is a 12 times thermal sight used to better identify the target vehicle. Once the CLU has been focused in WFOV, the gunner may switch to NFOV for target recognition before activating Seeker FOV. Seeker field of view. Once the best target area is chosen, the gunner presses one of the two triggers and is automatically switched to the fourth view, the Seeker FOV, which is a 9x magnification thermal view. This process is similar to the automatic zoom feature on most modern cameras. This view is also available along with the previously mentioned views, all of which may be accessed with press of a button. However, it is not as popular as a high magnification view. Takes longer to scan a wide area. This view allows the gunner to further aim the missile and set the guidance system housed inside the actual missile. It is when in this view that information is passed from the CLU, through the connection electronics of the launch tube assembly, and into the missile's guidance system. If the gunner feels uncomfortable with firing the missile, he can still cycle back to the other views without having to fire the missile. When the gunner is comfortable with the target picture, he pulls the second trigger and establishes a lock. The missile launches after a short delay. Lightweight CLU. The U.S. Army is developing a new CLU as an improvement over the Block I version. The new CLU is 70% smaller, 40% lighter, and has a 50% battery life increase. Features of the lightweight CLU are a long-wave IR sensor, a high-definition display with improved resolution, integrated hand grips, a 5-megapixel color camera, a laser point that can be seen visibly through IR, a far target locator using GPS, a laser rangefinder, and a heading sensor, and modernized electronics. Training. A great familiarity of each control and swift operation needs to be achieved before the unit can be deployed efficiently. American troops are trained on the system at the infantry school in Fort Benning, Georgia, for 2 weeks. The soldiers are taught basic care and maintenance, operation and abilities, assembly and disassembly, and the positions it can be fired from. Soldiers are also taught to distinguish between a variety of vehicle types even when only a rough outline is visible. The soldiers must accomplish several timed drills with set standards before being qualified to operate the system in both training and wartime situations. There are also smaller training programs set up on most Army bases that instruct soldiers on the proper use of the system. At these courses, the training program might be changed in small ways. This is most commonly only minor requirements left out due to budget, the amount of soldiers versus simulation equipment, and available time and resources. Both types of training courses have required proficiency levels that must be met before the soldier could operate the system in training exercises or wartime missions.